All right, so here we are with the Chapter 6 test review, and we're going to go through each of the problems. You can, of course, fast forward if you are going to a specific problem, but we will be moving through them linearly here. All right. So one thing that you're going to want to also have out is your Chapter 6 formula sheet, so being able to reference this first part, for instance, about vectors. All right. So we're given that point P is 611 and point Q is 48, and we're going to find the component form. Remember, that means with the pointy brackets, form of the vector, which is from Q to P. So if we go to our formula sheet, notice that, again, the initial point would have been Q, and the terminal point would have been P. So Q is x1 and y1, and the terminal point is x2, y2, because that's where the arrow points, even though it's really tiny, goes that way. All right, so then we're going to do our formula here, which says that in order to get the component form, we would take our x2 minus x1, and that would be with y2 minus y1. So x2 is going to be 6, and x1 is 4. Sorry, that's a minus sign. So 6 minus 4, and that's going to be in a coordinate with y2, which is 17, no, 11, minus 8. And so 6 minus 4 is going to get you 2, and 11 minus 8 is 3. If you end up doing it backwards and not considering the terminal point and the initial point, you're going to get negatives, but that's not what we're looking for. So positive 2, positive 3. All right. Then the next one is to find the component form from the vector. And so again, remember, component form is this in these brackets here. So they're telling us that the degree measure is 220, and then the magnitude here is 41. So if we know the degree and the magnitude, we're going to go ahead and, let's see, at least the way that I did it, okay, is to make this into a right triangle. And this right triangle has an angle here of 180 minus 220. So 220 minus 180 would get us this angle here. And that angle is going to be 40 degrees. And if we know that that angle is 40 degrees, we can use some trig to find out, for instance, what the opposite side length and the adjacent side length are. And so in that case, we can do, for instance, sine of 40, and that's going to equal our opposite, which is what we don't know, over our hypotenuse, which is 41. And then if we multiply the 41 times the 40, you'll cancel them there. And as long as you're in degree mode, because this is 40 degrees, we've got 41 times sine of 40, and we get 26.3543. So that's our opposite side, 26.3543. Then if we want the adjacent side, we're going to have to set up cosine. Oh, don't want to use that space. So we'll set up cosine of 40. And that's going to equal our adjacent, again, which we don't know. I'll call it A, over the hypotenuse, which is 41. Multiply everything by 41 again so that you can cancel them. And so if we multiply by 41 here, and then technically over here, which I'm running out of room, I'll get an A value of 41 times cosine of 40, again, in degree mode. And 41 times cosine of 40 is 31.4078. Alrighty. So in that case, we need to find the component form of the vector, and remember that the component form is the horizontal movement and then the vertical movement. And so our horizontal movement is going to be actually left negative 31, because we're going left, and then we're also going down, so that's also negative. And so the answer to this one is going to be the adjacent movement. So this one here, negative 31.41. And then the horizontal movement, so negative 26.35. And again, they're both negative because if we look at the picture, it's not actually 40 degrees, it's actually at 220 degrees. And so we do want to go left a certain amount and down, which will make them both negative. All right, moving on to finding the magnitude of the vector. When they give you a component form of that, it looks like if we want to find the magnitude, we can take A and B, which are the component form of a vector, and we can square A and square B, and that's going to give us our magnitude. So this is our A, this is our B, and it's equal to the square root of A squared plus B squared. And so that means that it's going to be the square root of negative 4 squared plus 6 squared. And so we're going to get 16 plus 36 in a square root, or 52. All right. And of course, we could reduce that a little bit if we needed to, but please don't put that into decimal form. So, all right. Then we need to find the direction angle for the vector and give the direction angle as an angle between 0 and 30 degrees. So again, this part here is trying to be that point form of an interval. So it's just saying that they want that angle between 0 and 360. All right, to the nearest tenth, looks like, so 1 decimal place. So if we want to find the direction angle, that's where we have to take our direction angle formula, which says it's tangent inverse of B over A, and then depending on where you are on the circle, you might have to add or subtract 180. So theta is equal to tangent inverse of B over A. And looking at our coordinate here, A is first and then B. And we may or may not need to add or subtract 180 to put it in its right position. So plugging that in, we're going to get tangent inverse of negative 5 over negative 3. And tangent inverse of negative 5 over negative 3 in degree mode. Leaves us with 59. Remember, we're rounding to the nearest tenth, so 59.0. Remember that we have to verify if this is where we actually are talking about here. So remember that negative 3, negative 5 is actually going to be in quadrant 3. And 59 degrees actually lands you up in quadrant 1. So 59 degrees is up here. We don't want that. We want it to go all the way over to quadrant 3. And so in that case, we're going to have to add 180. So if we add 180, that's going to leave us with 239.0. All right, and so that is our direction angle. Okay. The next one here, they're telling you that your vector u is 512. And we need to find the unit vector in the direction of u and write our answer in component form. So going back to what they're saying here, The unit vector takes the values that we already have for our horizontal and vertical movement and divides them by the measure of the magnitude. So that means that we're going to have to find the magnitude first. So we're going to use our formula here of magnitude is a squared plus b squared square rooted. So the magnitude of u with our a and our b gives us a squared, which is 5, plus b squared, which is 12. And so we're going to get 25 plus 144 that we're square rooting, which is the square root of 169, and that's just 13. All right, so that means that we are going to take both of our components here, 5 and 12, and divide them by the square root of 13. So we're going to have 5 13ths and then 12 13ths. And that is our component form answer. Again, you could have made those into decimals, but we try to avoid decimals as much as possible. So that is our unit vector in the direction of u and component form. All right, then we have this next visual of what's happening. A plane is flying in a direction of 285 degrees. So we've got a plane and it's flying in this path here in the dark line with an airspeed of 271. And so you'll notice that they labeled the a length, if you will, even though it's the magnitude or the speed, as 271. A wind from the direction of 37 degrees is blowing at 17 miles per hour. So notice that taking this angle and making it 37 degrees to the north there is going to now have a label of 17. And we need to find the actual ground speed and the direction of the plane. So we kind of have to do that by doing steps A, B, C, D, and E. All right. So the first thing that you're going to have to do is find the component form of the airplane vector. So the component form of the airplane vector asks you to find this vertical movement and then this horizontal movement to make a 271 degree hypotenuse. So since you're already going to use 270 degrees here, if we take away 270 from 285, that's a really small zero. 270 taken away from 85 leaves us with 15 degrees for this angle right here, which we'll just fill in, I guess. Okay. So 15 degrees is this angle right there. So that means that I have a right triangle with a hypotenuse of 271 and an angle measure up here of 15 degrees. And I need to find my adjacent side and my hypotenuse. So this is your adjacent side, and this is your opposite side. And so in order to find either of those, we can go ahead and use some trig. So let's see, to find the adjacent side, we're going to need cosine of that 15 degrees, and that's going to equal the adjacent over the hypotenuse. And then to find your opposite side, we're going to need sine of 15 degrees, and that's going to equal our opposite measure, which we'll just call P. Because it would be really weird to make it O, because O looks like 0, so no. All right. And just as we did in the previous problem, we're going to multiply both sides by this denominator. So this one's times 271 as well. This one's times 271. And then we'll find our measure of A. Let's see, where does it say? Any rounding? Nope. So we'll find our measure of A, or the adjacent side, or the vertical movement, as cosine of 15 times 271. All right, so the cosine of 15 times 271 is 261 point, we'll just go with one decimal place, 8. Actually, we're probably going to have to use this later, so let's just go with 4 decimal places, 7659. And then the p-value is going to be sine of 15 times 271, so that's 70.131400 because of the 2 nines. Alrighty. The component form of the airplane vector then is going to be a negative of what we did here. So a negative of the height, which is a. So we need a negative 261.7654. And then a positive, because we're going to the right, of 70.1400. That is the result for part A. All right. In part B, we need to find the component form of the wind vector. So the wind vector here, we're going to be talking about 17 as its hypotenuse. And then 37 degrees as its angle measure. And again, we need to find out what the opposite side is. So we'll label that as P and our adjacent side. So just as we did before, to find our answers, we're going to do cosine to find the A value. So cosine of 37 is going to equal A over 17. And then the other one is going to be sine of 37. And that's going to equal P over 17. And again, both of them to solve, you'll multiply by 17 so that those 17s cancel. And your answer in component form is going to be, let's see, they're both to the right and up, so that's fine. So A comma P. And AP is going to be this one here to find P. So P is sine of 37 times 17. So sine of 37 times 17 is 10.2309. So 10.2309 for that right part. And then the left part is your A value from up here. So 17 cosine of 37 in degree mode. And that's going to get you 13.5768. All right, so that is our component form of both of those vectors. So now that we have the component form of the wind and the airplane vector, we can find the component form of the resultant vector by adding them together. So if we add the two together, we'll get this light actual path here. And so the actual path vector is going to be the one from part A, which is in blue. So I'll just keep it in blue. So it's negative 261.7654 and 70.1400. And to that, we're going to add the other vector, which we just got to be 15.5768. And we'll also be adding the vertical movement, so 10.2309. All right, and so your actual path vector is going to be negative 261.7654 minus 15.5768. So subtracting these two digits, we're going to get our actual path vector of negative 277.3422. And then subtracting the 70 and the 10 gets you a vertical component of 59.9091. Alrighty, so just double checking let's see, down and over. You know what? I've made these backwards because it's clearly the horizontal first and then the vertical. So this is backwards. So your, let's see, vertical is first and then horizontal. Wait, am I doing it wrong again? Yes. All right, so this is your horizontal and this is your vertical. And so as a coordinate always goes, it's horizontal first. So sorry, this is 70.1400. And this one is negative 261 because we're still going down. 0.7659. Let's see if we did it wrong on this one as well. It's supposed to be to the right and up. So to the right and up. P is up, and that's this one. Okay, so that one's right. So we have to switch these around again. Okay. So instead we're going to do 70.1400 and negative 261.7659 because those are actually the vertical and horizontal movements. Okay, so 70.1400 minus 15.5768 gets you a horizontal movement of 54.5632, which again makes sense because we're following this actual path. And so we are going to have to go over this amount. And so the next number should be the -1. So negative 261.7659. Plus 10.2309. And realizing now that I subtracted the last one instead of adding it. Wow, I really apparently need to focus. Okay. All right, so 85.7168 is those two added because clearly that's what it's supposed to be. And then negative 251.535 is the second guy. Okay, geez Louise. All right, so the next one is the direction of the plane's actual path. And so that's going to go up to this guy, direction angle. And so we're going to do tangent inverse of b over a. And then depending on if we are actually in quadrant 4, we're going to add or subtract 180. So theta is going to equal the tangent inverse of b over a. And in both of these, our a is this value. And our b is this value. And so that means that we're going to do tangent inverse of our negative 251.535 over the 85.7168. Alrighty, so tangent inverse of 250 negative 251.535 divided by 85.7168. All right, so that's telling us that it is negative 71.1822. And technically that does get us into the quadrant, I guess it doesn't say anything about putting it in the 0 to 360. So this could be our answer. Or if you want it to be on the positive unit circle, you could add 360, because this is saying go this direction, 71 degrees, okay? But if we wanted the positive direction, we'd have to add 360 to that. And so in that case, we'd get 288.8178. All right, so if you want positive or negative, there you go. And then the ground speed, or the magnitude of the plane's actual path. And so in order to get the magnitude of this plane, now that it used to go 271 miles an hour, but then was hit by that 17-mile-an-hour wind, we just need to get the magnitude. So since we already have an A and a B, we're just going to find the magnitude. And so the speed is going to equal the square root of our A value, which is 85.7168 squared, plus our B value, which is negative 251.535 squared. And so 85.7168 plus negative 251 leaves us with the square root of 70617.2260. And so if we take the square root of that, we're going to get a ground speed of 265.7390. It did say that it was in miles per hour, so we'll do that. All right. So once I got my act together, those are the answers for that one. Guess I never boxed this one. All right. So that's page 1. All right. In page 2, going back to a little bit more of the basic vectors, they're telling us that vector u is negative 3, 2, vector v is 1, negative 5, and we need to figure out what this sum is going to be. So all we need to do is take a u and multiply by negative 3. Oh, sorry. And since that's just scalar multiplication, that means that you're going to distribute this negative 3 into both of these pieces. And so we're going to get positive 9 and negative 6 for this first version. The second thing is 2v, and so 2v is going to be 2 times 1 and negative 5 as a component form vector. So we'll just distribute that 2 and get 2, negative 10. Then we need to add them together, because that's what this is saying here. So if we add 9 and negative 6 to the vector of 2, negative 10, we're going to get 9 plus 2, so 11, and negative 6 and negative 10, so negative 16. All right. Then in the next one, they want you to do the dot product. Remember, this is not multiplication anymore when it comes to bolded vectors. So in that case, we're going to do our dot product, which has a formula over here. So you need to take the x value of the u vector and the x value of the v vector, multiply that, and add it to the y values being multiplied. So we're going to take, we'll call this u1 and u2 and v1 and v2. And so we're going to do u1 times v1 plus u2 times v2. So u1 is negative 4. That's going to be multiplied by 7 and added to negative 5 times negative 2. So negative 4 times 7 is negative 28, but then we're going to add 10 to that. So negative 18 is our dot product result. All right. Then we need to answer, is this orthogonal? And remember that if they are orthogonal, their dot product equals 0. And since negative 18 does not equal 0, A and B are not orthogonal. Okay. Then we're going to be using our work equation. So we've got weight cosine of the angle where the work is happening, and then times distance. So in this case, apparently a constant force of 15 pounds acting in the direction of 12,9 as our direction angle of an object 10 feet across, or sorry, it looks like up when we need to find the work. All right, so the weight or the force here is 15 pounds. So again, the work is going to come from the weight times cosine at the angle of the work happening times the distance. And our weight is 15 pounds. We do not know what angle measure yet, but we'll get there. And then our distance is 10 feet in this case. So we're going to take 150 times cosine of this angle measure. And how do we find that angle measure? We use our direction angle for that vector. So the direction angle is going to come from tangent inverse of the y component over the x component. So our side problem here is that we're going to do tangent inverse of 9 over 12. And that means that tangent inverse is going to result in 36.86. Whoops, that's an 89. 8699 degrees, apparently. And then just double checking, 12,9 is in quadrant 1 and 36 degrees rotation is in quadrant 1, so those work. So we just need to plug in 36.8699 right there. So 15 times cosine in degree mode of 36.8699 and times 10 gets us 95 point, whoa, that's a lot of nines. So we're just going to say 96. That's a weird 9. Okay. And our work is done in foot-pounds. All right. Okay. All right. The next one here wants you to find the graph of the given parametric equation. So if we're going to verify any of these working, we're going to need to put our calculator in parametric mode. Remember, if you don't have a graphing calculator, there's a link for that on HeadRush, so you can go to that. Plus, during the test, there will be the link at the top of the test page, so you can open it up then as well. So we need to be in parametric mode. All right. It feels like I didn't press that. Okay, I did. So the first things that we're going to graph here are not those. We're going to graph 7 sine of t, and t is our variable here, plus sine of 7t. And then the second graphing part is 7 cosine of t. Where is my there? Plus cosine of 7t. All right, and so before we graph, we are going to want to look at the window. And let's see, the window of most of these is not in degrees. Looks like it's in radians. So let's go ahead and go into our radian, because you can see that the axes here have whole numbers and not necessarily degrees going on when it comes to cosine. So let's see. So that's that. And then our t, I guess, I mean, we kind of just get to guess at this point. So we'll just go with whatever my calculator said there. The x's on these has some 6's and some 10's. So we'll just go negative 10 to 10. And then negative 10 to 10 for the other one too. All right, so let's see what we get here. Ooh, okay, so taking a look at each of these, it's either this one or maybe somehow this one. So the way that we can get it, for instance, to complete more is by taking our window and expanding our t, so maybe going to 5 instead of 3. And then to make it a little bit more rounded like these ones, we're going to have to change our t-step. So the smaller the t-step, the more likely it's going to be a fluid-looking graph. So there we go. And you can definitely see that we are going more for this image at this point. There you go. So that one, oh, sorry, we're up here, but either way, same images. This is going to be our graph. And as you graphed in parametric mode, we're going to just write down that our window had a t-min of -3 and a t-max of 5 and a t-step of 0.1. And then your x and y were -10 to 10. All right. Then we're going to graph number 12. I hope it's this one. All right, because that one's funky. So our next equations are going to be 10 sine of t plus 4 sine of 6t and then 10 cosine of t minus 4 cosine of 6t. All right, it's a lot of typing. We can use the same window as we had last time because it's probably going to reference that. And even though my window is a little bit small for what's happening here, what was the scale? Oh, that's a 16. Oh, well, fine. We will go to -16 then. All right, so if we graph based on what this one was giving an image of, we do end up having A. And so if we just take note, our window was a t minimum of -3, a t maximum of 5, and a t step of 0.1. And then your x and y were between -16, whoops, and 16. All right, so that's those guys. All right, then we're going to eliminate the parameter, and the way the parameter is t, it's mentioned in here. So that just means that I want to rewrite this so that it's y equals. So in order to make it y equals, I'm going to want to write this one as t equals so I can put it in here for t. You could do it the other way and solve this one for t, but you have a squared, so it's a little bit harder. You'll have 2 answer equations. We don't need that. So if it's multiplied by a half, we can multiply by 2 over 1. It's reciprocal in order to eliminate the half. And so we have t equals 2x, technically over 1, but no thanks. And then we're going to take this idea and plug it in to this equation. So we have y equals 3, and then inside the 2x squared minus 6. So 2x is being placed in for the variable up here. Then we do want to simplify as much as possible. So this squared being applied inside of these parentheses is going to make 4x squared. That will ultimately be multiplied by 3 and subtracting a 6. And 3 times 4 gets you 12. So we're going to go with 12x squared minus 6. So if you graph this, or if you graph these two in parametric mode, or this in your function mode, you will get the same image. So apparently a parabola. All right. Then we get to plot a little bit. So going back to our reference of how to plot something. First thing is going to be how many circles you're going out, and then the second one is your rotation. And if it's a positive, you're going to go in the, let's see if I can remember the words, counterclockwise. But if it's negative, you're going clockwise, which always seems backwards in my head. All right. So from number 14, that means that I'm going to go out to the fourth circle. And then from there, I'm going to rotate 2 pi over 3. So 2 pi over 3 is apparently covered up in here. So it's this 2 after pi over 2. So 2 after pi over 2 leaves us with this. All right, so that's where your dot should be and nowhere else. Okay. Then number 15 wants you to plot 2 4 pi over 3. So 2, and then 4 pi over 3 is all the way over here. And so making sure that we're 2 circles out. Sure. And then the last one wants you to go negative 1.5. So 1 circle and a half is here. But then take that and rotate negative 120 degrees. So remember, negative is clockwise. So negative 120 degrees is going to be 180 is this whole thing, but 120 means we went back 60. So we're going to rotate all the way over to 60, because between 60 and 180 is 120 degrees. And so that is our point right there. Just erasing that one to make sure that we didn't keep it. All right, so those are our 3 plotted points. Then the next thing is that each of these, and now this one, has 4 options that it could be. It actually has infinite if you go outside of a unit circle rotation. In fact, that's what they're doing here with negatives. So we're going to name 4 pair of polar coordinates that represent this point. So if we take a look at it, it is on the 3rd circle out. So if I want to, I'm going to probably start using 3s, but then also negative 3s to get there. And now we get to determine our angles. So starting from 0, the first one's at 150. So 3, 150. Then rather than going 150 this way, we can actually go backwards around here. So if we go backwards around here, we have 180, but then another 30 degrees, so 210. And negative. So we're going that clockwise direction. All right. Then if we go negative 3, and then easily going up that 30 degrees, remember that's clockwise, so that's negative 30 degrees. And then if we go negative 3, we could also go all the way around 330 degrees. Again, we're going in that counterclockwise direction, so it is positive, as we mentioned earlier. All right, so those are all the options in this set of circles. Again, it's always try the positive radians and going down or up, and then trying the negative radians and around or up. All right, then you need to find the rectangular coordinates that match these polar coordinates. So going back over here, we have polar coordinates of x and y. Oh, sorry, these are polar coordinates, so they are r and theta. and we need to get x and y, so we get to use these equations here. So x is going to be r times cosine of, apparently they've decided it's t, which is weird, but that's theta, plus x1. And then the y is our sine of theta. And I guess I'm not really sure why we have these anymore. That's not there. Oh, here. Oh, that's a circle equation. Okay, hi. Let's look over here. X is our cosine, got it, and y is our sine. Okay, that's that part of it. Super. So now we can take our r, which is -8, and multiply by our cosine of 240. And then also take -8 for our r and multiply by sine of 240. Notice this is in degrees, and I note that my calculator was already in radians, I think. Yep. So let's go back to degrees. And we're going to do -8 times cosine of 240. All right, and so that's going to be 4 for our x value. And then -8 times sine of 240 is going to get 6.9282. So that means that our coordinate is 4, 6.9282. So that's the rectangular coordinates matching these polar coordinates. So if I graphed this point on this graph and then this point on a traditional graph, we would get in the same point. How interesting is that? All right. Then our last page here of the review wants you to find the polar coordinates whose rectangular coordinates. So now we're going backwards from what we had before. So rectangular coordinates have your x and your y. And going back to our formula sheet, we need to use this in order to get back to the polar coordinates. So in order to get the r value, we're going to either have plus or minus x squared plus y squared. So our r is going to be either plus or minus, depending on what we're looking for, of -1 squared plus -square root of 3 squared. So we're going to have 1 plus 3. And that means plus or minus the square root of 4. Our theta is going to be tangent inverse of y over x from the formula, and then maybe plus or minus 180 depending on what's happening. And so that's going to be tangent inverse of y, so -square root of 3 over -1, which is just going to be positive. So tangent inverse of the square root of 3 is 60 degrees. And remember that we may or may not have to add or subtract 180. So going back to this original xy coordinate, if we go negative and then negative, we're in quadrant 3. So we need to force these values to get us over into quadrant 3. So notice that we only have 60 degrees potentially, so it might be nice to actually just go negative to begin with, and then 60 degrees in the positive direction. So if we go -square root of 4, which is totally 2, been a long week here. Okay, so -2. And then we rotate 60 degrees from that. We're going to end up in this area. So in that case, 60 degrees there. Anyway, so that's what our coordinate is going to be. -2 and a positive 60 degrees. You could have potentially done a +2 and then 60 plus 180 to go here, but negative 260, and again that goes kind of back to every coordinate has 4 options, so something that makes this is perfectly acceptable. All right, then we're going to use our grapher to determine which of the graphs match the given polar equation and then state the name of the graph. So you can use the grapher, or of course you can use the fact that we know what a rose curve versus a limousin versus all of the options here. But to double check that we know how to graph on our grapher, we make sure we are in polar mode, and I think radian is a little easier to work with when we're doing graphing. So our graph is going to be 2 minus 2 sine of theta, which is the x, and our window, it seems, has x's and y's that are going to 4. That's a very interesting number. Okay. So let's see. We're going to do at least 1 rotation, so that's 2 pi. And we're going negative 4 to 4 in our x's and y's. All right, so if we graph that, hopefully our step is enough to get this. Looks like we are going to end up with part C here. Ours looks more like a tomato because it's not a squared image here. So that's your C. And then remember that this one here is limousin because it says what is the graph name. Because it kind of looks like a lima bean. You could also call it a cardioid because it's kind of got this heart shape. So that also happens. It's just a subset of the same one. All right, and then the next one has 3 sine 2 theta as our equation. So 3 sine 2 theta. Definitely going to be, our flower one here and not here. So in that case, we're going to put C as what 23 is. And then the name of this one, even though it looks more like a flower than a rose, is a rose. And then our last one, putting in 1 plus 2 cosine of theta. Gives us an image. Of a very convex, this guy here, most convex limousin. And so that's this one, A. Okay. Yeah. So those are that guy. All right, so that's the end of our test review. So hopefully that helps you out for the Chapter 6 test that we are going to be having on Monday via Google Docs.